A recurrence relation is a way to define a sequence by saying how each term depends on earlier terms. And so a classic example is the Tower of Hanoi puzzle. So we have 3 pegs and a stack of n disks. So you have these 3 pegs here, and you have n disks. In this picture, we see 4 of them. And the goal is to move the entire stack to the 3rd peg, to this target peg. So you would like to put this configuration here. And there are 2 rules. So first, we can only move 1 disk at a time. So you need to take the top disk of one of these 3 pegs and move it somewhere else. And second, you can never place a larger disk on top of a smaller disk. So this disk over here, the second one, can never go on top of the first one. It can go on top of the 3rd one and the 4th one. So the question is, what is the smallest number of moves needed to solve the puzzle with n disks, right? So what is the smallest amount of moves to solve this? Now, the key idea here is to think recursively. So suppose we know how to solve the puzzle with n-1 disks. Then to solve the puzzle with n disks, you can do the following. So the idea is that you started here, and in this example here we see 4 disks. And so to solve the puzzle, you essentially want to put the 3 disks here, and then the big one, put it over here, and then these 3 disks, move it again over here. So essentially, if you know how to solve the 3-disk puzzle, you're able to solve the 4-disk puzzle by just solving the 3-disk puzzle for the intermediate, then moving the bottom disk over here, and then solving the 3-disk puzzle again. And so this gives you a recursion. So this is true in general. So this gives you a recursion that to solve the amount of moves that you need to solve the n puzzle, so we're going to denote this by Tn, is going to be equal to 2 times the n-1 plus 1. Why? Because you first have to do Tn-1 to put this over here. Then you have one step. This one here is just the bottom disk going all the way over here. And then this Tn-1 here, the n-1 disks, you need to move them again, and that's Tn-1. So it ends up being 2Tn-1 plus 1. And you have an initial condition. So of course, if you only had 1 disk, you can solve it in 1 move, right? If you just move the disk here. And so this here, this recurrence, you're able to calculate all the values, right? Because you start at 1, and then the next one is going to be 2 times the previous plus 1. And so this is a recursion. So let's try to see if we can find the closed form for this recursion. So again, this is our recursion. Let's try to first guess a formula for this. So we can start by computing some values. So of course, I'll put it here for completeness. T1 is just equal to 1. T2 is going to be equal to 2 times T1 plus 1. And so this is 2 plus 1 equal to 3. So it's 2 times 1 plus 1 equal to 3. T3 is going to be 2 times T2 plus 1. So this will be 6 plus 1, 7. T4 will be 2 times T3 plus 1. So 14 plus 1, 15. And from here, you could already try to guess a formula. So if you look at this, it looks like, so you can think of this as 2 to the power of 0, sorry, 2 to the power of 0, no, 2 to the 1 minus 1. This could be 2 squared minus 1, 2 cubed minus 1, and 2 to the power of 4 minus 1. And of course, this could just be a coincidence. We could check for T5. What would we expect? If it follows the rule, then 2 to the 5 would be 32, and then minus 1 would be 31. And so let's see, this would be 2 times T4 plus 1. So this is going to be 15 times 2, 30, plus 1, 31. And so indeed it is 2 to the 5 minus 1. So that means that we have a conjecture. So our conjecture, it's not a proof, our conjecture is that Tn might be 2 to the n minus 1, right? Okay. How can we prove this? So one way to prove is by induction. I mean, now we have a guess, and we could maybe try to use induction. And we saw induction works quite well when you have recursion involved. And so this will actually be the case, and you can prove it by induction. So once again, how do we do an induction proof? Well, we start first by the base case. So the base case, in this case for n equal to 1, which we already computed, but for completeness here, t1 is equal to 1, equal to 2 to the 1 minus 1. And so, okay, it works. So for the base case, it's true. And now we need to do the inductive step. So what is the inductive step? So we're going to assume the formula is true for k, and then we're going to show that it's true for k plus 1. So here we're going to use the regular induction. We're not going to need strong induction. So assume true for n equal to k. And so what does this mean? Well, this means that tk is equal to 2 to the k minus 1. And now we need to show that this will hold for n equal to k plus 1. So then for n equal to k plus 1, we have, so let's see. So tk plus 1 is equal to 2 times tk plus 1. And we know by our induction hypothesis, so this follows from the recursion, and now from the induction hypothesis, tk is equal to 2 to the k minus 1. Okay, so this follows from our inductive hypothesis. So this is going to be 2 times 2 to the k minus 1 plus 1. And so this will be equal to 2 to the k plus 1 minus 2 plus 1, which is just 2 to the k plus 1 minus 1. So indeed, it does hold true. It is true that 2 to tk plus 1 is 2 to the k plus 1 minus 1. And so thus the formula holds for k plus 1. And thus we just conclude by induction. Oh, let me write this better. By induction, the formula is valid for all positive integers